Okay. So, today I shall discuss some aspects of superstring theory, especially what is called the BRST operator. So, the BRST operator enables us to separate out the physical states from the non-physical states. So, what is the physical state? Separate out the physical states from the non-physical states. So, first we observe that if we look at the string, if you look at the string energy momentum tensor, you write it as ln e power I n sigma n varying over all z. That is, you take the energy momentum tensor of the string, the plus plus component, expand it as a Fourier series, and ln's will be quadratic forms in ln's will be of the form summation alpha minus n, alpha minus m dot alpha n plus m summed over n. They will be like this for n varying over all z, where when you write alpha n dot alpha L, I mean simply alpha mu n, alpha mu L. Alpha mu's are the creation, for alpha mu n's for n positive are the annihilation operators of the bosonic string, and alpha n for n less than 0 are the creation operators. So, this is a quadratic form in the bosonic Fourier series. So, you have the bosonic string which has been expressed as x mu plus p mu tau plus summation minus I times summation n not equal to 0 alpha mu n by n e power I n tau minus sigma. I left moving a right moving bosonic string, and from the basic canonical commutation relations between the x mu's, namely if you look at the canonical commutation relations, x mu of tau sigma comma dou tau of x nu of tau sigma dash, this is equal to I eta mu nu delta sigma minus sigma dash. The basic bosonic canonical bosonic commutation relations that came by from the Lagrangian of the string. We start with the Lagrangian of the string as given by L is half dou alpha x mu dou beta x mu eta alpha beta, where eta alpha beta is the Minkowski metric on the string space, and I have adopted a gauge fixing method as discussed earlier, in which the string worldsheet metric by means of a reparametrization and a conformal transformation has been brought to the form 1 0 0 minus 1. There are other parameterizations, there are other so eta alpha beta is this sort of a matrix, so that this becomes simply dou tau square x mu dou tau x mu dou tau x mu minus dou sigma x mu dou sigma x mu into half. It can also be written in this way. So, you can always choose a a gauge fixing method by integrating out over in the path integral over the worldsheet metric after incorporating after inserting appropriate delta functions, and bring the metric to this form, and then you derive from this you define the momentum operator as phi mu, which is dou L by dou x mu dou tau x mu, and this comes out to be equal to simply dou tau of x mu. So, you apply the canonical commutation relations between position and moment and get this. So, if you substitute this expression for this Fourier series expression into this commutation relations, you get the bosonic commutation relations, namely alpha mu n comma alpha nu m is equal to I n eta mu nu delta n plus m are the bosonic commutation relations. They are harmonic oscillators. When mu and nu are when mu and nu are 0, it is plus 1, and otherwise it is minus 1. So, some sort of a negative energy bosonic oscillators, they correspond to the transverse states correspond to. So, if you now substitute for, so T plus plus of sigma, the energy momentum tensor is a quadratic form, this is half summation alpha minus m dot alpha n plus m, but this is defined everywhere, this is defined for all n's except when n is 0. When n is 0, there is a ambiguity in the ordering, because alpha minus m does not commute with alpha m, does not commute, whereas all the other alpha n's are 0. Alpha k comma alpha l is 0 for k not equal to minus l. So there is an ambiguity, and that ambiguity leads to an anomaly in the sorry, this is okay, this is L, this is Ln, and T plus sigma is nothing but Ln e power in tau minus sigma over n. So when m equal to 0, when n equal to 0, there is an anomaly, and so if you compute the using the bosonic commutation relations, the commutation between Ln and Lm, that will come out to be n minus m Ln plus m plus some Cn multiplied by delta n plus m. This is due to the anomaly, and you can determine this Cn by applying the Jacobi identity, namely Ln comma Lm comma Lk plus Ln Lm comma Lk comma Ln plus Lk comma Ln comma Lm equal to 0. If you apply this Jacobi identity, you get a difference equation for the Cn's, and if you solve the difference equation, you get Cn to be of the form C1 n cube plus C2 n, right, if you solve the difference equation. So the question is how do you determine the constant C1 and C2. So the first method, let us say it is a d dimensional string, so that you go from 0 1 2 up to d minus 1, and eta 0 0 is 1 and eta 1 1 eta 2 2 eta d minus 1, they are all minus 1 anyway. So suppose you apply the relation say L1 comma L minus 1, if you look at this and you look at it in the vacuum state, you apply this to the vacuum state and compute this in two different ways. So first, for example, if you look at L minus 1, what is it equal to? It is equal to half summation alpha minus m alpha m plus 1. Sorry, if you look at L, okay, L okay, yeah, L minus 1 is this m minus 1 summed over all m varying over integers, or all m varying over integers, half of this m varying over integers. So if you see now the vacuum state is annihilated by the annihilation operators. So you cannot have, if you look at a term like alpha minus m into alpha m minus 1, look at this, or let us look at it this way, let us look at L minus 1 comma L1, or let us look at it, okay, L1 comma L minus 1 0 0. So if you evaluate it L1 L minus 1 0 0 minus 0 L minus 1 L1 0, so this evaluates to this, and if you look at L minus 1, it is a sum of alpha minus m dot alpha m plus 1, alpha m minus 1. So for m less than z, summed over all the m's varying over z. So for m equal to, if m is greater than 1, if m is greater than or equal to 1, m greater than or equal to 1, these are annihilation operators and they will annihilate the vacuum. So they will give a 0 contribution. If m is less than or equal to minus 1, if m is less than or equal to minus 1, then this is positive, minus m is positive, and the two commute with each other, because minus m plus m minus 1 is not 0. So you can bring alpha m to this side and that will annihilate the vacuum 0. So the only term which can contribute is when m equal to 0. That means that when you have alpha 0 dot alpha minus 1, so that can contribute to this term in L minus 1. Likewise, since L minus 1, since L1 is equal to L minus 1 dagger, this will also get a contribution only when L1 is of the same form. So if you could you can write 0 L1 as L minus 1 acting on 0 dagger conjugate. So if you where dagger denotes adjoint, so here you will get alpha 0 alpha minus 1, so here you will get alpha minus 1 dot if you take the dagger of the, if you take L1 is L minus 1 dagger, so that will give you, it will give you a term like alpha 1 dot alpha 0, alpha 0, then here you will have alpha 0 dot alpha minus 1 and then 0 here you put, that is what this term will contribute. And if you this will give the only non-zero contribution. So, if you slide this, if you slide alpha 0 to this side by a commutation, alpha 0 comma alpha minus 1, alpha 0 acting on 0 is 0 because it is a vacuum state, there is nothing there in it. So, that will become 0. So, it will not contribute anything, right. Alpha 0 will commute with alpha minus 1, you can slide in alpha 0 and bring it here, and alpha 0 acting on 0 is 0 because what is alpha 0? Alpha 0 is simply p mu, alpha mu is p mu tau, that is equal to p that is equal to alpha 0 of tau, alpha 0. Alpha 0 tau corresponds to p mu, and x mu comma p mu is I eta mu nu. So, this is the ground state in which all the oscillators and the ground are in the ground state, and the center of mass alone of the center of mass of the string alone is moving with a momentum p mu. So, it will contribute to nothing. So, this term cannot give anything. What about L minus 1 with L 1? If you look at L minus 1 0, L minus 1, L 1 0, if you look at this term, then again you can have what is L 1? L 1 is a linear combination of half alpha minus m dot alpha m plus 1. So, if m is greater than or equal to 0 or greater than or equal to minus 1, it is not going to contribute. If m is greater than or equal to 0, alpha 1 will be an annihilation operator which will annihilate 0. If you look at m equal to minus 1, or if you look at m equal to minus 1, that will give you alpha 0. If you look at m equal to minus 2, if you look at m equal to minus 2, then you will get half alpha 2 dot alpha minus 1, and alpha minus 1 alpha 2 acting on 0 will also give you 0. So, so this whole thing evaluates to 0. If you see this whole thing will evaluate out to 0, that means this will also be 0 because alpha 2 will annihilate the vacuum. And if you look at, if you put alpha m as 0, this will give you alpha 1, and alpha 1 will annihilate the vacuum. If you put m as minus 1 alpha 0, that will also annihilate the vacuum. So, you get the result that 0 L 1 comma L minus 1 0, that must be 0. On the other hand, from the commutation relations you have L 1 comma L minus 1 is equal to 2 L, the difference 2 plus C1n plus C2n cube into delta n plus m, delta n plus m. Here you are putting n as 1. So, this will be C1 into 1 plus C2 into 1 cube. So, C1 plus C2, it will give you a C1 plus C2 term into delta n plus m. So, delta n plus m is 1 plus delta 1 plus 1, which is 0. So, this will give you this thing, and L2, if you look at 0 L2 0, that will also be 0 by the same logic, because L2 is a linear combination of half alpha minus m dot alpha m plus 2. So, and for any m, either m plus 2 is positive or minus m is positive. So, that will annihilate the vacuum. So, you get the result that C1 plus C2 0 0 is 0. In other words, C1 plus C2 is 0 or C2 equal to minus C1, right. So, you get the result that C2 is minus C1, and so the Virasoro commutation relations can be written as n minus m L n plus m plus C1 n minus n cube delta n plus n. So, it now remains to determine the constant C1, it remains to determine the constant C1. If you look at L2 comma L minus 2 and compute this quantity in the vacuum expected value of this quantity, on the one hand this is the difference of 2 minus 2, which is 4 into L0. Sorry, I made a mistake in the last calculation, it was L1 comma L minus 1, which is the difference, which is 2 L0, n plus m is 0 plus C1 plus C2, C1n plus C2n cube, and L0, the vacuum expected value of L0 is 0, right, because L0 is the energy. In the ground state, what is L0? L0 is nothing but half p square plus summation n alpha minus n dot alpha n, and for any n, either n not equal to 0. For any n not equal to 0, either n is positive or minus n is positive. So, in either case, and alpha minus n will commute with alpha n, with alpha n will not, okay, alpha, if you choose, if n is positive, then alpha n will annihilate the vacuum. If n is negative, then minus n is positive, right, the difference, okay. So, in either case the vacuum expected value of this quantity must be 0 in the ground state, because p square, vacuum expected value of p square in the ground state is 0 in the vacuum state, and alpha minus n, alpha n, if you look at, say for example, alpha minus n dot alpha n, and look at this in the vacuum state, then what do you get? If n is positive, then alpha 1 0 is 0, if n is negative, then if n is negative, then if n is positive, then this will also become 0. So, just check this, that L1 comma L minus 1, L1 comma L minus 1 is a difference into L0 plus this, but if you use a normal ordering, you are using a normal ordering for L0, and so you assume that this is the normal order, that means all the annihilations come to the right. So, in that case this will have a 0 vacuum expectation value, that is, there is an ambiguity in defining L0. If you use the normal ordering convention for defining L0, then you put all the positive alpha n's to the right, for all positive n's you put alpha n to the right and you put this to the left, you will only be subtracting a constant which may be an infinite constant in the process of making this choice. So, L0, so you see that the normal ordered version of this will have a vacuum expected value of 0. So, that is why C1 comes out to be minus C2, or C1 plus C2 is 0. If you look at the vacuum expected value of L2 comma L minus 2, 0, what is this? This is 0, L2 L minus 2 0, minus 0 L minus 2 L2 0. Now, what is L2? L2, you see, you want to get a creation operator acting on this to be non-zero. L minus 2 is a linear combination of alpha minus m with alpha m minus 2. So, if m is greater than or equal to 2, it will be 0. If m is if m is 0, it will give you alpha minus 2, but here you will get an alpha 0 which will commute with this, and it can be pushed to the right, and that will annihilate the vacuum. So, the only non-zero contribution can come when m is minus 1, in which case you get when m is 1, in which case you get alpha minus 1 dot alpha minus 1. If you put 1, you get alpha, if you put m equal to, if you put m equal to 1 here, this will be alpha minus 1 and this will be alpha minus 1. So, here you get alpha minus 1 dot alpha minus 1. If m is less than, if m is minus 1, here you will get alpha 1 which can be pushed to the right, because alpha minus m and alpha m minus 2 commute, because minus m plus m minus 2 is non-zero. So, the only non-zero term can come from this, whereas if you look at L2, L2 is a linear combination of alpha minus m and alpha m plus 2, and you are acting here on by 0 to the left, you are acting this to the left by 0. So, if m is positive, then minus m is negative and this will annihilate the vacuum. If m is 0, again it will annihilate the vacuum. If m is minus 1, then this will give you alpha 1, this will give you alpha 1 dot alpha. If m is minus 1, this will give you dot alpha 1. If m is minus 2, then this is alpha 2, but whereas if m is minus 2, then this will be, if m is minus 2, this is alpha 0 and this will commute to the left and annihilate the vacuum 0, right, because if you put m as 0, if you put m as minus 1, then this is alpha 1 and alpha 1 commutes with alpha minus, if you put m, see alpha minus m will commute with, alpha m plus 2 for any m. So in that case if you put m as minus 1, this will be alpha 1, and alpha, if you put m as minus 1 here you get alpha 1, and that will annihilate the vacuum. If you put m as minus 1, then if you put m as minus 1, then here you get 0. If you put m as minus 1, then you get an alpha 1 which will not be 0, because its conjugate will be alpha minus 1 acting on 0, which is a creation operator acting on 0, which will be non-zero. If you put m as 1, then this is alpha minus 1 and its conjugate will be 0, because it will be alpha minus 1 conjugate is alpha minus 1 conjugate is alpha 1. If you put m as if you put m as 1, if you put m as minus 1, if you put m as 1, then of course if you put m as 1, then this will annihilate. If you put m as negative, say minus 2, then alpha 0 will be here and that will annihilate it. If you put minus 3, again you get alpha minus 1 and that will annihilate 0. If you put, so for all m less than or equal to minus 2, this will commute to the left and it will annihilate the vacuum. So this is the only non-zero term which contributes to this. So when you compute the product of these two, the only non-zero term which can come here is that alpha 1 dot alpha 1 dot alpha minus 1 dot alpha minus 1 and then 0. Now how to evaluate this? So the easiest way to evaluate it is to push alpha 1 to the right by using the commutation relations. So first you see that alpha 1 will commute with alpha minus 1, okay, alpha 1 will commute with alpha minus 1 to give you alpha 1, let us write it in this way, 0 alpha 1 dot alpha 1, then alpha minus 1 dot alpha minus 1, 0. So that will give you 0. This means this is a shorthand notation for alpha mu 1, then alpha nu minus 1, alpha nu minus 1 and then 0. So you commute this alpha mu comma alpha mu 1 comma alpha nu minus 1, this is equal to delta nu mu, then you put n is 1 and the sum of these two which is 0. So you will commute this with this, so you will get a non-zero term like alpha mu 1 and here you get delta nu mu and then you will get alpha nu minus 1 and then 0 0. The other term which after commuting alpha mu will come to this side, so it will give you alpha mu 1 with alpha nu minus 1, again you commute with these two. So you will push alpha mu, you will be able to push alpha mu, you will be able to push alpha mu, you can do it in this way also, you can do it as alpha mu 1 comma alpha nu minus 1 alpha nu 1 minus 1, you are looking at this commutator. So this is alpha mu 1 comma alpha nu minus 1 into alpha nu minus 1 plus alpha nu minus 1 into alpha mu 1 comma alpha nu minus 1, which is equal to, this will give you eta mu nu into alpha nu minus 1 and this will give you plus delta nu mu into alpha nu minus 1. So this is nothing but twice alpha mu minus 1, right. So this is nothing but 2 alpha mu minus 1. So if you look at this, what you have a picture of alpha mu 1 and alpha nu minus 1 and vacuum expected value of this. So if you commute this by this, you will get alpha mu 1, the commutator of this with this is nothing but, as we just saw, twice alpha mu minus 1 and then 0 and 0. You see, when you write say xy 0 0, this can be written as 0 x comma y 0 plus 0 y x 0. So that x is here alpha mu 1, when it commutes to the right this will become 0 because x is an annihilation operator. So you will be left with just this much. Now again you use a commutation relation to push this to the right, so to push this annihilation operator to the right. So you are using alpha mu 1 comma alpha mu minus 1, this quantity is nothing but delta mu mu which is equal to d, your delta mu, how many dimensions are there? There are d. So, this is equal to d. So, that is how the dimension of the string enters into the picture, into this relation. So, you get 0 twice, then here you will get d 0, which is 2d, right. So, if you look at 0 L2 comma L minus 2 0, that will be equal to I think 4d at constant times d times, that will be equal to constant, it will be 4d or 2d, just let us check it. So, on the other hand this is 4d, because you are using both of these terms will contribute, L2 L minus 2 and L minus 2 L2. Now, if you compute this in another way using the commutation, Virasoro commutation relations, that gives you 4, the difference of this into the 0 plus C naught, C into n minus n cube with n equal to 2, at n equal to 2. So, 2 minus 2 is 2 minus 8. So, that is 6 minus 6c, and if you put n as 2, this is minus 6c. So, this will give you on the other hand minus 6c, and the value of c will come out to be equal to just check 2, if you put n as 2 you get 2 actually this should be d by 2, because you are taking half of this, right. L2 comma L minus 2, what is Ln? Ln is equal to half summation alpha minus m dot alpha m plus n. So, you have to take a factor of 2 into account, it is 2d, otherwise if you divide by 2, you are taking this factor 2 into account in both the places L2 and L minus 2. So, you have to divide by 1 by 2 into 1 by 2 or 1 by 2 square. So, 1 by 2 square, that will give you d by 2. So, you get that d by 2 is equal to minus 6c, or equivalently d equal to c equal to minus d by 12, So, in other words, you get the Virasoro commutation relations as Ln comma L minus n is equal to d by 12, sorry, this is equal to n minus m, no, it is Ln comma Lm is equal to n minus m into Ln plus n plus d by 12 into n cube minus n. These are the into delta n plus m. These are the Virasoro commutation relations. These are the Virasoro commutation relations. Now, you can also do this for the Gauss field. Okay, you can also do this for the Gauss field. You have to determine the critical dimension d. I want to prove that d is 26 is the critical dimension. There are various ways of proving this. One is to construct a family of 0 norm states, that is physical states which are orthogonal to themselves, 0 norm physical states. Of course, the spurious state is a state which is orthogonal to all the physical states. So, to construct a one parameter family of 0 norm states and look at the critical value of the parameter, look at the value of d at which this number of 0 norm states becomes very large, okay, and then you get the value of d equal to 26. Let us just see how we can go about doing it. Suppose you define a physical state to be Ln, a state which satisfies this, n greater than 1 and L0 phi is equal to a phi. That is, it is an eigenstate of the Hamiltonian and it is annihilated by the positive frequency components of the energy momentum tensor. And what is a non-physical state? A non-physical state is one in which one of these is violated, one of these conditions is violated. So, suppose you consider L minus n, okay, L minus n chi n, this sort of a state. Okay, if you construct a state of this form, summation n greater than or equal to 1, suppose you construct this sort of a state, then can I make this orthogonal to every physical state? You see, suppose phi is a physical state and you look at this relation, what is this? Chi n is some state and I am constructing this state ln summation n greater than or equal to 1 L minus 1 chi n, and I am constructing this inner product here, but L minus n dagger is equal to ln, that is because alpha mu minus n dagger is alpha mu n, they are creation annihilation pairs. So, I can push all the L minus n's to this side and write it as summation ln n greater than 1 phi with chi n, but ln phi is 0 for n greater than or equal to 1 because phi is a physical state. So, this is orthogonal to all the physical states. So, this gives you an example of a spurious state, right. So, if you look at this chi is equal to n greater than 1 L minus n chi n, this is a spurious state, but I also want this to be an eigen function of the energy corresponding to the eigen value a equal to 1. Okay, I want this to satisfy the condition L0 chi equal to chi, that is I am choosing a as 1. So, how do I get that? Suppose you act L0 L minus n chi n, if you do this, this can be written as L0 comma L minus n plus L minus n L0 acting on chi n, but L0 comma L minus n is the difference, this minus n is n into the sum L minus n plus L minus n L0 acting on chi n. Now, L minus n acts on chi n multiplied by n, but L0 acts on chi n to give you L0 acts on chi n to give you some b chi n, let us say L0 acts on chi n to give b n chi n, suppose these are eigen states of L0, then this equation can be written as n plus b n multiplied by L minus n chi n, and you want this to be equal to 1 because you want chi to be an eigen state of L0 with eigen value 1, that means you want b n plus n to be equal to 1 or equivalently b n equal to 1 minus n. So, this is same as saying that L0 chi n must be equal to 1 minus n chi n or equivalently L0 plus n minus 1 chi n is 0, this must give you 0, right. Then L0 plus n minus 1 chi n equal to 0. So, you have L0 plus n minus 1 chi n, this must be 0, that means the spurious state can be written as summation L minus n chi n, this gives you a family of spurious states, call this as chi, where chi n satisfies this equation for each n. So, this is orthogonal to every physical state, in particular it will be orthogonal to itself. Now, you can see that it is enough to write it as L minus 1 into chi 1 plus L minus 2 into chi 2, right. If it is of this form, then automatically it will be orthogonal to all the physical states, and it can also such a state can also be put in this form, that is because you can use the commutators, you have ln comma lm is equal to n minus m ln plus m, if n plus m is not 0, that is the anomaly is absent. So, you can write down for example L minus 3 as L minus 1 comma L minus 2 apart from a proportionality of constant of proportionality, this is proportional to this. L minus 4 is L minus 1 comma L minus 3, which is L minus 1 comma L minus 1 comma L minus 2, which is also L minus 1 comma L minus 1 comma L minus 1. So, if you look at for example, if you represent the state in this way, then this is also the most general form, it is all any state of this form can be represented in this form, because for example, if you have a term like L minus 3 acting on chi 3, that can be written as L minus 2 comma L minus 1 acting on chi 3 apart from a constant of multiplicative constant of proportionality, and you can write L minus 2 as You can write this as L minus 2 L minus 1 chi 3 minus L minus 1 L minus 2 chi 3. So, this is something, this is of the form L minus 2 times some state plus L minus 1 times some other state. If you have L minus 4 comma chi 4, this can be written as L minus 1 into L minus 3 chi 4 minus L minus 4 minus L minus 3 L minus 1 into chi 4. Remember they all commute, L minus 3 commutes with L minus 1, but L minus 3 acting on this can be written as L minus 1 comma L minus 2 into L minus 1 into chi 4. So, again this can be brought into this form. So, a general spurious state can be written in this form. A general spurious state can be written as L minus 1 chi 1 plus L minus 2 chi 2, where L0 plus n minus 1, L0 plus n minus 1 chi n is 0 for n equals 1 and 2, right. This is a general form of a spurious state. Is this clear? Now, now you look at a state of the form say L minus 2 plus gamma L minus 1 square acting on chi, something like this. Okay. My claim is that this is a spurious state. Obviously, it is a spurious state because it is of this form L minus 1 times something plus L minus 2 times something. This is a spurious state. Now, I want this to so this is orthogonal to all the physical states. Now, I want this state, say let us call this as eta or let us call this as psi. Psi is a spurious state. You want this to make it spurious, it must be an eigen function of L0 with eigen value 1, right. So, this must be an eigen state of L0 with eigen value 1. If you look at L0 acting on L minus 2 chi, what is this? You use a commutator. This is nothing but L0 comma L minus 2 plus L minus 2 L0 acting on chi, but L0 comma L minus 2 is the difference 2 into the sum L minus 2 L minus 2, L0 acting on chi is 1 acting is some b acting on chi, right. So, let us say L0 acting on chi is some b acting on b multiplied by chi. So, this is plus b into L minus 2 chi. So, this is nothing but b plus 2 into L minus 2 chi, right. L0 acting on L minus 2 chi is b times L minus 2 chi. What about L okay b plus 2 L minus 2 chi, b plus 2 into L minus 2 chi, L0 acting on psi, L0 acting on L minus 2 chi is given by this, and you are defining the state to be psi as L minus 1 L minus 2 plus gamma L minus 1 square acting on chi. So, if you look at L0 acting on L minus 1 square chi, what is it? What is this equal to? You want to make this an eigen state of L0 with eigen value 1. So, this can be written as L0 comma L minus 1 square plus L minus 1 square L0 multiplied by chi, but this is nothing but L0 comma L minus 1 into L minus 1 plus L minus 1 into L0 comma L minus 1, this commutator, and L0 comma L minus 1 is the difference. So, 1 times L minus 1. So, what is 1 L minus 1? So, L minus 1 square it will give you again here, and here you get L0 comma L minus 1 is again L minus 1 square. So, this will give you twice L minus 1 square. So, this is nothing but twice L minus 1 square. So, this quantity can be written as twice L minus 1 square plus L minus 1 square L0 into chi, but L0 acting on chi is b into chi, So, this can be written as b plus 2 into L minus 1 square chi, right, where chi satisfies L0 chi equal to b chi. So, if you look at L0 acting on psi, if you add these two contributions, both L minus 2 chi and L minus 1 square chi are eigen states of L0 with eigen value b plus 2. So, this is nothing but b plus 2 times psi, and you want this to be equal to b plus 2 should be 1, that means b must be minus 1, because it should have the same energy, which is A equal to 1 as a physical state. So, in other words, if you choose B as 1, that means if you choose your B as minus 1, if you choose B as minus 1, that means L0 acting on chi should be minus of chi, and you define the spurious state to be equal to L minus 1, L minus 2 plus gamma L minus 1 square acting on chi. Then psi becomes an eigenstate of L0 with the same energy as, namely 1 A equal to 1 equal to psi, and at the same time psi is spurious, psi is also spurious, because if you take the inner product of psi with any, if you take the inner product of psi with any physical state, then it will L minus 2 will come to this side, this will be L2 phi with chi plus gamma times L minus 1 square L plus 1 square, it will become after taking the adjoint L plus 1 square phi with chi, and L1 acting on phi is 0, L2 acting on phi is 0. So, this will give you 0. So, you see that this quantity, now you can ask the question, when does this have 0 norm? So, this has got 0 norm if it is orthogonal to itself, okay, it has got 0 norm if it is orthogonal to itself, and it is orthogonal to itself because it is orthogonal to L2 times anything plus L1 times anything. Now, you want to determine the critical value of gamma, you want to determine so this gives you a spurious state, and this gives you a spurious state, and it is orthogonal to itself because it is orthogonal, is it orthogonal to itself? It is orthogonal to every physical state phi, but for it to be orthogonal to itself it should be annihilated by L2 and L1, L2 and L1, it should be annihilated by L2 and L1, right. You want this to be a 0 norm state, that means you want psi comma psi to be 0. You see, whenever a state has 0 norm, then it is something like it being gauge, it has a very large number of gauge symmetries, right. When a state has 0 norm, then it has a very large number of gauge symmetries. So, 0 norm states imply that the system has a large number of gauge symmetries, right. So, we are looking at the critical value of D at which this will have a large number of gauge symmetries. Obviously, if you want psi with psi to be 0, then you are looking for something like L minus 2 square chi, L minus 2 square chi, sorry L minus 2 chi plus gamma L minus 1 square chi must be orthogonal to psi, which is same as saying that chi with L2 psi plus gamma chi with L1 square psi must be 0. So, this will happen if L1 psi is 0 and L2 psi is 0, right. So, you are looking for a situation in which you have a spurious state defined by L minus 2 plus gamma L minus 1 square acting on chi with L0 acting on chi being given by minus chi, so that it guarantees that L0 acting on psi will be psi, that is, it has got the same energy as required for a physical state, but it is spurious, and you also require that L2 psi must be 0 and L1 psi must also be 0 for it to be spurious, for it to have 0 norm, So, equivalently, if L0, you see, if L0 acting on this gives you L0 acting on psi gives you psi. So, it is a physical state, but it should be orthogonal to it should be annihilated by L2, it should be annihilated by L2, it should also be annihilated by L1. Why? Because you want it to have 0 norm. It is orthogonal to all the physical states. Of course, a spurious physical state will be orthogonal to itself, but this is only a spurious state as yet, it is not a physical state. So, it is orthogonal to all the physical states, but we want it to be orthogonal also to itself. So, we require L2 psi to be 0 and L1 psi to be 0. Just compute now, L1 acting on L minus 2 chi, you want L1 acting on psi to be 0. So, L1 acting on L minus 2 chi, this is nothing but okay, you require this to be a spurious state. So, you want L1 acting on this to be 0, so that it becomes a spurious physical state. If L1 acting on psi and L2 acting on psi are 0, then all the L3, L4, L5 all these acting on psi will be 0, because the L3 can be written as L3, L4, L5 can be written as multiple commutators of L1 and L2. So, we require that for this to be a spurious physical state, you want this to be 0, and you also want L1 L minus 1 square acting on chi to be 0. So, you are of course given the you are also given the condition that L0 plus n minus 1 chi. So, L0 plus just try to see what is happening here. L1 acting on L minus 2 psi is nothing but L1 comma L minus 2 plus L minus 2 L1 acting on chi. L1 acting on L minus 2 is the difference. So, 3 into L minus 1 plus L minus 1 L1 acting on chi. L0 acting on chi is equal to minus chi. So, that will guarantee this. Now, if L1 acting on chi is 0, then this gives you 3 L minus 1 chi, right. This gives you 3 L minus 1 chi, am I right? This gives you, if you assume that L1 acting on chi is 0, L1 acting on chi is 0, then this gives you 3 L minus 1 chi. L1 acting on L minus 2, L1 acting on L minus 1 square, L1 acting on L minus 1 square acting on chi is nothing but L1 comma L minus 1 square into chi, because L1 acting on chi is 0, but L1 comma L minus 1 square is L1 comma L minus 1 into L minus 1 plus L minus 1 into L1 comma L minus 1, and L1 comma L minus 1 is the difference to L0 L minus 1 plus L minus 1 L0 acting on chi. Right. Just try to see what we are saying. We want psi to be an eigenstate of L0 with eigenvalue 1. So, that will be guaranteed if L0 chi equal to minus chi, that we have seen already, but you also want it to be a spurious physical state. So, L1 acting on this must be 0 and L1 acting on psi must be 0 and L2 acting on psi must also be 0, right. So, you have L0 chi equal to minus chi, that guarantees that L0 acting on psi will be psi, and your psi is given by L minus 2 plus gamma L minus 1 square acting on chi. So, you computed L1 L minus 2 acting on chi, that is nothing but L1 comma L minus 2 acting on chi, which is equal to 3 L minus 1 acting on chi, and L1 acting on L minus 1 square acting on chi, this is L minus 1 L0 plus L0 L minus 1, the commutator of L1 with L minus 1 square acting on chi, and this is nothing but L0 acting on chi is minus chi. So, this is minus L minus 1 chi plus L0 comma L minus 1, L0 comma L minus 1, L0 comma L minus 1 plus L minus 1 L0 acting on chi, and L0 acting on L minus 1 is the difference L minus 1 acting on chi, L0 comma L minus 1 is L minus 1, L0 acting on chi, L0 acting on chi is minus chi. So, that minus chi will this will give you minus L minus 1. So, these two will cancel out, this will give you simply minus L minus 1 chi, minus L minus 1 chi. right. So, you get 3 L1 acting on L0 is this plus L minus 1 acting on L0, L0 acting on L0 comma L minus 1 is the difference 1 into L minus 1. So, L minus 1 acting on chi, L minus 1 acting on chi is L0 acting on chi is minus chi. So, that will give you a factor of gamma s. What will it give you gamma s? It will give you if you look at L minus 1, this is L minus 1, L0 acting on chi is minus chi. So, here you got L0 comma L minus 1 plus L minus 1 L0, L0 acting on chi is minus L minus 1. So, minus 2 L minus 1 and L0 acting on minus 1 is the difference, should get a factor of 2, L1 acting on L minus 2, L1 acting on is 3 L minus 1. So, 3 L minus 1 chi plus gamma times it will be 2 gamma L minus 1 chi minus 2 gamma L minus 1 chi, because there is a minus 1 which comes from here and L0 acting on L minus 1 is L minus 1 plus L minus 1 L0, L minus 1 L0, L0 acting on chi, L0 acting on chi is minus chi. So, L minus 1, you will have a factor of minus 2 gamma minus 2. So, in other words, for this to be I want L1 acting on this should be 0. So, you will get the factor gamma equal to 3 by 2. Just work it out again, you have defined psi as L minus 2 plus gamma L minus 1 square acting on chi, and you want L0 psi to be psi. So, it means that L0 and so you are asking what should L0 acting on chi be. Suppose L0 acting on chi is b times chi, suppose this is of this form, then if you act L0 on this you will get L0 comma L minus 2 plus L minus 2 L0, L minus 2 L0 is plus b into L minus 2 acting on chi. Here you will have plus gamma times L0 acting on L minus 1 square plus L minus 1 square L0, which is this into b acting on chi. L0 acting on psi will come out to be this, and L0 comma L minus 2 is the difference 2 into L minus 2 plus b into L minus 2, which is b plus 2 into L minus 2, b plus 2 into L minus 2 plus L0 comma L minus 1 square is L0 comma L minus 1 into L minus 1 plus L minus 1 L0 comma L minus 1, and L0 comma L minus 1 is the difference L1 L minus 1 plus L minus 1 L1. Now, L1 acting on chi is 0, you are assuming that L1 acting on chi is 0, why so? L1 acting on chi, because you want this to be annihilated by L0 acting on L1, L minus 1 the difference, this is L0 comma L minus 1 is L the difference of this L1, this is this is 0 minus minus 1 which is minus 1. So, this is L minus 1 square twice L minus 1 square, this is twice L minus 1 square. So, so this is plus b plus 2 L minus 2 plus b plus 2 L0 comma L0 comma L minus 1 square is twice L minus 1 square. So, b plus 2 gamma, it is plus b plus 2 gamma, b plus 2 just let me work it out again, L minus 2 plus gamma L minus 1 square acting on chi, you are defining this to be psi and you are allowing L0 acting on psi to be b psi, sorry L0 acting on L0 acting on chi, you are allowing this to be equal to b times chi. So, you get L0 acting on L minus 2 acting on chi as a commutator of these two, which is twice L minus 2. So, 2 plus b into L minus 2 chi, the first equation, and L 0 acting on L minus 1 square acting on chi, the commutator, it is twice L minus 1 square. So, L minus 1 square plus L minus square into L 0 plus b into L minus 1 square acting on chi, which is b plus 2 into L minus 1 square acting on chi. So, in other words, L 0 acting on psi, if you add these two equations, multiply this equation by gamma and add to this, you will get L 0 acting on psi is nothing but b plus 2 times psi, and you want this to be equal to psi. So, you must take b as minus 1, right. So, choose b as minus 1. So, you choose L 0 chi to be equal to minus of chi, and then you are constructing the state as L minus 2 plus gamma L minus 1 square acting on chi, and you want L 1 acting on psi to be 0, want it to be orthogonal to the physical states. So, that an L 2 acting on psi, that must also be 0, then automatically L 3, L 4 they will all act on psi to give 0, because they can be written as multiple commutators of L 1 with L 2. So, you want L 1 psi to be 0. So, you want L 1 acting on L minus 2 chi, you want this to be 0, and you also want L 1 acting on L minus 1 square chi, you want this also to be 0, or rather you want a linear combination of this to be, you want this to be, okay, you want this to be orthogonal to all the physical states, that means it must be a spurious physical state, it must be a spurious physical state, because it is orthogonal to all the physical states and this is satisfied. So, if you take the commutator of these two, this will give you 3 into L minus 1 plus L minus 2 L 1 acting on chi. So, this is nothing but 3 L minus 1 acting on chi. If you say, assume that L 1 acting on chi is 0, if you assume that L 1 acting on chi is 0, you get this. What about L minus 1 square? If you say L 1 L minus 1 square with chi can be written as L 1 comma L minus 1 square with chi, because L 1 acting on chi is 0, but this will give you the difference. So, it will give you the difference L 1 comma L minus 1 into L minus 1 plus L minus 1 into L 1 comma L minus 1. So, the difference, so L 1 comma L minus 1 will give you twice L 0, it will give you twice L 0 into L minus 1. L 1 comma L minus 1 is, what is L 1 comma L minus 1? L 1 comma L minus 1 is twice L 0, because the anomaly will cancel out. Anomaly is d by 12 into n cube minus n into delta n. If you put n as 1, this becomes 0. So, the anomaly will cancel out in the case of 1 and minus 1. So, twice L 0 L minus 1 plus twice L minus 1 L 0 acting on chi. This can also, now L 0 acting on chi is nothing but minus chi. So, this can be written as twice L 0 L minus 1 minus twice L minus 1 acting on chi. So, you can see immediately that L 1 acting on L minus 1 square, L 0 acting on L 0 acting on L 0 acting on L minus 1, again you use a commutator here, L 0 comma L minus 1. So, you write it as twice L 0 comma L minus 1 plus L minus 1 L 0, okay, and L 0 comma L minus 1 is simply twice L minus 1, twice L minus 1, and that will give you L minus 1 L 0 plus twice L minus 1 L 0, L 0 acting on chi is minus. So, minus 2 and minus 2 into this. So, it will give you a factor of 2, right, you will get gamma as 3 by 2, you will get gamma as 3 by 2. So, you will get psi as L minus 2 plus 3 by 2 into L minus 1 square acting on chi. Now, you put the condition that L minus 2 should also annihilate this, L 2 should also annihilate this, L 2 psi must be 0. If you put this condition, then you get L 2 L minus 2 plus 3 by 2 L 2 L minus 1 square acting on chi. this must be 0. Let us say you want L2 acting on L minus 2 chi, you want this to be 0. So, if you take the commutator, this can be written as L2 comma L minus 2 plus acting on chi, because L2 acting on chi is anyway 0, L2 comma L minus 2 is 4 L0. So, it is minus 4 chi, it is minus 4 chi. So, you get minus 4 into chi and plus 3 by 2 acting on 3 by, sorry, when you take L2 comma L minus 2, it is not just 4, L2 comma L minus 2, there is an anomaly term also, this is the difference 4 L0 plus d by 12 into n cube minus n, 2 2s are 2 cube is 8, 8 minus 2 6, so into 6, so that will give you 4 L0 plus d by 2. So, that will give you 4 plus L minus, L minus 2, L2 comma L minus 2 is the difference, 2 minus 2 is 4, 4 into L0 is this, plus d by 2 into chi, plus d by 2 into chi, that is what 4, so it will give you minus 4 chi plus d by 2 chi, plus 3 by 2 gamma, 3 by 2 L2 with L2 acting on L minus 1 square acting on chi, that is nothing but L2 comma L minus 1 square acting on chi, because L2 acting on chi is 0, this is nothing but L2 comma L minus 1 into L minus 1 plus L minus 1 into L2 comma L minus 1 acting on chi, but L2 comma L minus 1 is the difference 3 into L1, 3 into L1 into L minus 1, L2 comma L1 plus 3 L minus 1 into L1, L1 acting on chi is 0, so that will not give anything. So, it will give you plus 3, so it will give you 3 by 2 into L2 acting on L minus 1 is 3 into L1 into L minus 1 acting on chi, but you can write this as L1 comma L minus 1 because L1 acting on chi is 0. So, this can be written as the difference 3 by 2, the last term is 3 by 2 into 3 into the difference is 2 L0, L0 is minus acting on chi is minus chi. So, these are 9, it will give you 9, right. So, it will give you minus 9, this will give you, this whole last term will give you minus 9. So, you get minus 4 plus d by 2 minus 9, acting on chi must be 0, right, minus 4 plus 9 by plus d by minus 4 plus d by 2 minus 9 acting on chi must be 0, or in other words d by 2 minus 13 equal to 0 or d equal to 26. The magical figure of d equal to 26, d is equal to 26 is the critical dimension at which there is a very large number, there is a very large number of 0 norm states. Okay. Repeat of the calculation, you are considering the 0 norm states L minus 1, L minus 2 plus gamma L minus 1 square acting on chi, this is psi, you put the condition that L1 chi equal to 0, L2 chi equal to 0, and you require that you want L1, you also put the condition that L0 acting on chi, L0 acting on chi is minus chi. So, this will guarantee that L0 acting on psi, is equal to psi. Then you apply L1 acting on L minus 2, you compute L1 acting on L minus 2 chi, you want this to be 0 because you want this to be orthogonal to L1 to the range of L1, you also want this to be orthogonal to the range of L2. So, you also require that L1 acting on L minus 1 square chi, you need the sum of these two, you do not need this, what you need is that L1 acting on L minus 2 plus gamma times L minus 1 square acting on chi. You want this to be 0 and you also want to have L2 acting on L minus 2 plus gamma L minus 1 square acting on chi. You want this also to be 0. So, if you take the commutator here, you get L1 comma L minus 2, because L1 acting on chi is 0 and L2 acting on chi is 0. This is equivalent to saying that L1 comma L minus 2 plus gamma L minus 1 square acting on chi, this must be 0, and also L2 comma L minus 2 plus gamma L minus 1 square acting on chi, this must be 0. So, L1 comma L minus 2 is 3 into L minus 1, 3 into L minus 1 plus gamma times, here you will have L1 comma L minus 1 into L minus 1 plus L minus 1 into L1 comma L minus 1, that is what this will give you. So, 3 L minus 1, this acting on chi. So, this will give you 3 L minus 1 plus L1 comma L minus 1 is the difference. So, gamma times 2 into L0 into L minus 1 plus L minus 1 times L1 comma L minus 1 is 2 L0, and this acts on chi, this whole thing acts on chi. So, this equation is equivalent to this equation, this must be 0, which is same as saying that I can again apply a commutator here. So, this is 3 L minus 1 plus 2 gamma, I can write this as L0 comma L minus 1. So, L0 comma L minus 1 plus L minus 1 L0, 2 gamma into this plus 2 gamma into L minus 1 L0 acting on chi. So, this will give you 3 L minus 1 plus L0 comma L minus 1 is the difference. So, 1 into L minus 1. So, 1 into L minus 1, the difference is 1 into L minus 1. So, plus 2 gamma into 1 into L minus 1 plus L minus 1 L0, but L0 acting on chi is minus, L0 acting on chi is minus chi. So, this will give you minus L minus 1. So, this will give you an L minus 1, this will go minus L minus 1, and this will cancel out this term. Whereas, if you look at L minus 1, if you look at 3 L minus 1 plus 2 gamma acting on L minus 1 L0, right, 3 L minus 1 plus 2 gamma L minus 1 L0, okay. L minus 1 L0 acting on chi is minus chi. So, this will give you a factor of, this will give you 3 L minus 1 chi, and this will give you a factor of 2 gamma into L0 acting on chi is minus chi. So, minus L minus 1. So, this will give minus L minus 1. So, it will give you finally 3 minus 2 gamma, 3 minus 2 gamma acting on chi, that must be 0, which is equivalent to saying that gamma is 3 by 2. So, that comes out to be okay. And second part, if you require that L2 acting on L minus 2 plus gamma L minus 1 square acting on chi, you require this also to be 0, that means you take the commutator here and require this to be 0, then you get finally D equal to 26, as we just saw in the previous slide. Now, I shall talk a little bit about BRST operators. BRST operators, how to separate out the physical states from the non-physical states. So, you define an operator Q to be equal to summation A n k, I just make clear what I am trying to say, ln into Ck, n n k varying over z plus summation A1 A2 n k m into Cn Ck Bm, where the Cn's are the ghost field Fourier series coefficients. Cn's and Bn's are the ghost field Fourier series coefficients. What does this mean? Your Cn, Bn, n contained in Z are ghost Fourier series components. You see, what we are happening is that what is happening here is the following: you have S times the bosonic action depending on the metric, and you are taking a path integral dx like this, and you want this to be when you apply a gauge fixing method, that is, you transform, you start with a metric, the standard metric 1 0 0 minus 1, and apply a gauge transformation and conformal transformations to arrive at an arbitrary metric, and then you do gauge fixing. That means you use the condition that delta H plus plus delta H minus minus dH integral dH plus plus dH minus minus, this must be 1, right. You insert this factor into this and then you integrate, as we saw last time, by using the fact that if you make a small reparameterization, then delta H plus plus, the change in the metric will be nothing but del plus acting on xi plus, and delta H minus minus will be 2 del minus acting on xi minus, and delta H plus minus will be del plus acting on xi minus plus del minus acting on xi plus. So, by inserting this delta function, we showed last time that we could bring this path integral to a standard form, that is, you could forget about, you could assume that H was the standard metric and you are integrating only over the string variables. If you assume, if you make this, this is called gauge fixing, and in the process what we did was we had to introduce an extra term to take into account the determinant of the factor del plus and del minus. That is, when you transform this integral by writing it as dH plus plus by d xi plus, write it as this by d xi plus, the determinant, and dH minus by d xi minus into d xi plus d xi minus. So, these determinants will give you factors of twice determinant of delta plus and twice determinant of delta minus, and delta plus delta minus determinants could be expressed by adding extra. So, you have a term like delta plus, you could write this as e power integral c plus sigma del plus b plus c plus b plus sigma d2 sigma into dc plus db plus. You could write this as a ghost integral, you could write this as an integral fermionic or Berezin integral, you could replace the determinant by this. Similarly, for delta minus, this amounts to adding an extra term to the Lagrangian, to the bosonic action. That means you take the action half dou alpha x mu dou beta x mu eta alpha beta, you take this ghost action, you take this bosonic string action and add to this an extra action which is nothing but c plus into dou plus b plus, or rather dou minus it should have been dou minus b plus plus c minus into dou plus b minus, to take into account both. This will give you determinant of delta minus. You see, what is happening is that when you look at del minus, in the absence of any metric, del minus is dou minus, which is dou tau minus dou sigma, whereas b plus sigma depends on tau plus sigma, right. So, tau, if you and the field equations are simply, if you look at this action, the field equations for b plus are del minus b plus is 0, or equivalently del minus b plus is 0 and del plus b minus is 0. That means this is an agreement with the fact that b plus depends on only tau plus sigma. So, automatically it will satisfy this field equation, right. So, you add these two extra terms to the action and then you compute the energy momentum tensor of this whole bosonic field and ghost field taken together, and you compute this Fourier series coefficients. In the end, what will happen is that, for example, if you look at c plus dou minus b plus c minus dou plus b minus, if you look at this is the ghost Lagrangian, so I call it as Tg, let us call this as Lg, L ghost is given by this. You compute the ghost energy momentum tensor. So, what will it be? It will be Tgh, let us call it as Tg simply to abbreviate things, Tg. So, what are the different components? Dou Lgh ghost by dou minus b plus into dou minus b plus, this will give you T minus minus for ghost, Tg minus minus. Likewise, if you take dou Lg by dou minus b plus into dou plus b minus, that will give you T minus plus, which is same as you are choosing a metric as 0 1 minus 0 1 1 0, it is a symmetric metric, right? 0 1 1 0 we are choosing this as the metric, conformally fixed metric, conformally and reparameterization fixed metric after gauge fixing. So, this will give you T minus plus, which is this is same as T ghost plus minus, this is same as T ghost plus plus, right. And if you look at, since dou minus B plus is 0 by the field equations, when the field equations are satisfied, which is also called the on shell condition, on mass shell condition, when on mass shell conditions are satisfied, that means the field satisfies the equations of motion, then Tg plus minus will become 0, because dou minus acting on B plus is 0 and you will get just Tg plus plus, and this will give you, if you take dou Lg by dou minus B plus, that will give you C plus. So, this will give you C plus into dou plus B minus, sorry, it will give you this will give you dou plus B minus, just let me check once again. Here you have dou minus B plus, dou by dou minus B plus into dou minus B plus, dou minus B plus is 0. So, you have dou plus B plus, not dou minus, this is dou plus B plus, which is C plus dou plus B plus, right. Similarly, so you get T ghost plus plus to be equal to C plus dou plus B plus, and likewise Tg minus minus is C minus dou minus B minus. So, you add these two energy momentum tensor components to the energy momentum of the bosonic string, then you will get an equation of the form, you will get the total energy momentum tensor of the bosonic field and the ghost field, that is equal to T plus plus is given by dou plus x plus dou plus x plus. Just try to see how do you compute the energy momentum tensor of the ghost field. We have already seen, of the ghost field we have seen that this is nothing but C plus dou plus B plus, that is Tg plus plus, plus you have to add to this energy momentum tensor of the bosonic field. The bosonic Lagrangian was what? Bosonic Lagrangian was half dou plus x dot dou minus x. So, dou Lb by dou plus x, dou minus x into dou plus x, this will give you nothing but half dou plus x dou plus x. This is equal to T minus plus for the bosonic field, which is same as T plus plus for the bosonic field if you lower the index minus using the metric, using the worldsheet metric. So, the total energy momentum tensor T plus plus component of the energy momentum tensor is nothing but, this one is nothing but half dou plus x dot dou plus x plus C plus dou plus B plus, and since dou plus x minus is 0, dou plus x minus is 0. So, you can replace this by dou plus x plus, then only the left moving part of x, you can look at it from this point. Likewise, you can get an expression for T minus minus b, the minus component of the energy momentum tensor of the bosonic field plus the ghost field, and then you expand C plus, these are fermionic fields now. So, you look at, for example, C plus dou plus B plus sigma, this is Tg plus plus. So, you expand your and of course, they are satisfying the field equations, this is 0 and dou minus B plus is also 0. So, they will have solutions as C plus sigma, which is summation Cn e power In, since it is plus it will depend on tau plus sigma. Likewise, B plus sigma will be summation Bn e power In tau minus sigma. So, if you now tau plus sigma. So, if you now look at the ghost Lagrangian, it is C plus dou minus B plus, this is the ghost Lagrangian, and if you write down the field equations you get dou minus B. So, what is the momentum corresponding to B plus? You have to take dou Lg divided by dou 0 B plus, that will give you C plus, because dou minus is simply dou tau minus dou sigma. So, when I say 0 it means dou tau I am taking here, dou tau differentiation with respect to tau. So, you get the canonical momentum as this and you get the anti-commutation relation. Since these are fermions, ghosts are fermions, you get the canonical anti-commutation relations, namely B plus tau sigma comma C plus tau sigma dash. This anti-commutator is delta sigma minus sigma dash. So, if you substitute for C plus sigma into this equation, this Fourier expansion, then you get the simple relation that Cn comma Bm anti-commutator is nothing but delta n plus n. And then you look at the ghost energy momentum tensor, namely C plus into dou plus B plus integral d sigma. No, you do not integrate it, this you integrate later. You call this as T, we have called this already as Tg plus plus. You expand this using the Fourier expansions of C plus and B plus. You expand this, so you will get summation Cn e power in sigma multiplied by dou plus. So, it will give you in into Bn e power in sigma summation n, that is dou plus. So, if you write this n, you can write it as summation n minus m into Cn Bm, Cn B n minus, sorry, it should be, if you look at the Fourier, if you take the product of this and look at the coefficient of e power in sigma in this product, you will get summation n minus m, here you take Cm, here you take Bn minus m. So, Cm Bn minus m. So, these play the role of the Virasoro operators for the ghost fields, right. So, I call this as LNG, So, these are the ghost Virasoro operators, just as you had the bosonic Virasoro operators as the Fourier coefficient of, as the Fourier series coefficients of the energy momentum tensor for the bosonic field, like so. So you see that your LGN is nothing but summation over all m n minus m Cn Bn minus m, and likewise Ln is summation half over all m alpha n alpha m alpha minus m dot alpha n plus m, and the ghost fields commute with the bosonic fields. So, you call this as LGB. So, you look at now LNB plus LNG, the total Virasoro operator for the total energy momentum tensor, call this as Ln. Then we have already seen that Ln boson has an anomaly. Similarly, you can show that the ghost fields also have an anomaly. So, you can show that LGN comma LGM is of the form something times LGN plus m, something times LGN plus m plus an anomaly, and if you look at the total anomaly in Ln, namely Ln comma Lm is nothing but L boson this plus LGN comma LGM, and if you add these two terms and you will get an anomaly, and you want to cancel out that anomaly can be cancelled only when d is 26. This is the result of cancellation. So, that much is about this. Now, I wanted to discuss something about BRST operators before you do this, that is a way of separating out the physical state from non-physical states. So, I consider an operator Q of the form summation nk A1 nk into Ln into Ck plus summation A2 nkm into Cn Ck Bm nkm. So, now you also consider the ghost number operator U, which tells you the fermion number. So, that is C minus n Bm. This is the ghost number operator. It tells you the, since Cn and Bn's are, since C minus n is the conjugate of Bn as regards creation and annihilation operators. So, if Bn is a creation operator for the nth mode, then if Bn is a creation operator for the nth mode, then C minus n is the annihilation operator for the same mode, and vice versa. So, you can see very easily that your Q you can see from this from the anti-commutation relations of the ghost fields, you can see that q comma u is equal to I think it is minus u. Just check this, if you it is either plus or minus u, you can write this as qu minus uq minus uq, qu minus uq is equal to plus or minus u, or equivalently qu is equal to u into q, u into q, no, it should not be u, this will be plus or minus q, plus or minus q, this will also be plus or minus q, plus or minus q. Why is it coming out to be plus or minus q? Because if you commute this with u, you see your Cn's will, your Bn will cancel out one of the Ck due to the commutation anti-commutation relation. So you will be left with Ln with C minus n, which is precisely of this form, and similarly if you commute this with this, then C minus n will cancel out one, C minus n will cancel out a Ck here, and a B, so you will be left, and a Bn will cancel out a Cn. So you will be left with Bn with B, see a Bn will cancel out a C, a B here will cancel out a C, and a B here will cancel out a C. So so you will be left with q, just try to see, if you look at the commutation relation between a q and a u, one of the b's will cancel out the c here, so you will be left with ln c minus n, which is precisely of this form of this term, it is a term of having this form. If you look at the commutation relations between this term and this term, this cubic term and this term, what will happen is that a bn will cancel out, a b will cancel out a c, so you will be left again with two c's and a b, which is precisely of this form, provided you choose your a1 and a2 appropriately. So this can also be written as qu is equal to u, it is u plus or minus 1 into q. So actually it turns out to be that it is a plus 1, it is a plus 1, right. So you can write this as a plus 1 here. So in other words, if you take a state phi and you act on it by u, or you act on it by qu, I think it should have been minus 1 here, just check this, you have q comma u is equal to minus q, which is same as saying qu minus uq is minus q, which is same as saying q into u plus 1, q into u plus 1 is equal to uq. The same as saying that uq acting on phi will give you q acting on u plus 1 phi. So if phi is a ghost state, if phi has got a ghost number of k phi, that is phi is an eigenstate of the ghost number operator with eigenvalue k, then you can see immediately that qu will be an eigenstate of the ghost number operator with an eigenvalue of k plus 1 into q phi. That means q creates an extra ghost number, q takes a state of ghost number k to a state of ghost number k plus 1, it creates a ghost number extra. Now you can also see that suppose and also you can show that q square equal to 0 by appropriate choice of the a1 a2 coefficients, that means q is a nilpotent operator. So you can talk of the cohomology generated by u, cohomology generated by u by q, because it is a nilpotent operator, it consists of all states of the form q phi, any state of the form psi plus q phi is equivalent, belongs to the equivalent class of psi, right. So closed states mean that q psi is 0. So obviously if it is of the form q phi, then q acting on this is 0 because q is nilpotent, this is q square acting on phi, which is 0. So you can speak of the cohomology generated by u, just as you talk about the cohomology in the case of differentials on the exterior product space, right. So q can be, so any state which satisfies q psi equal to 0 can be called a closed state, and any state which is in the range of q can be is 0 in cohomology, So, now what I want to prove is the following result, fundamental result, that a state is physical if it has got when a state has 0 ghost number, when a state has 0 ghost number, that means it does not contain any ghost, then it is physical if it is left invariant by q, that means if it is a closed state for q, that means q acting on that psi should be 0, then it is a physical state, and it is a spurious state if it has got cohomology 0, that means it is in the range of q. So, you can look upon the physical states as states which belong to the cohomology class of q, non-zero cohomology class of q, and the spurious states as those which belong to the 0 cohomology class of q. Anyway, let us just see how we go about proving these results. So, you look at a state having 0 ghost number, that means C acting on phi is 0 and Bn acting on phi is 0 for all n greater than or equal to 0. So, they have 0 ghost. When they have 0 ghost, you expect them to be non-anomalous. So, if you look at such a state and you write down q phi equal to 0, the condition for it, if you write the condition for such a state to be invariant, then you see how did you construct the q's? You constructed the q as a1 nk ln ck plus summation a2 nkm cn ck cm bm. So, you are choosing the a1 and a2 appropriately. So, it will turn out that this will be, if you make the assumption that Cn and Bn phi are 0 for n greater than or equal to 0, then only the negative terms, those terms involving C minus n and B minus n will contribute, and you can show that this will be of the form summation C minus n ln So, q phi equal to 0 will give you a condition. If you take this into account, q phi will give you the condition that if you put the condition that it is BRST invariant, you will get a condition that it is of the form that the vanishing of this means that ln phi must be 0 for all n greater than or equal to 1, and L0 minus 1 phi, that must be 0 by using the structure of the constants a1 and a2. You can show that this will be of this form, that is, you will have this will be of the form summation so it will be of the form summation L minus n Cn, this term will be of this form, and since Cn's annihilate phi for positive n, this will contribute only when n is negative, or equivalently those terms with C minus n for n greater than or equal to 1, only they will contribute to the action on phi. That means ln acting on that phi should be 0, because Cn acting on phi's are 0 for n greater than or equal to 1. So, it will so q acting on phi will have a contribution from here only when you take those values of n for which C minus for which n is positive, that means C minus n for n greater than or equal to 1, and they will appear in the combination C minus n ln, where ln and n's are greater, n you are summing over n greater than or equal to 1, that means n ln phi should be 0 for n greater than or equal to 1, that will give you the condition for physicality, and L0 minus 1 phi equal to 0, that will also give you this condition. Now, if you look at the states which are of the form q phi, say suppose a state is in the range, let us say a state phi, let us say a state psi is in the range it is in the range of q, that means it is 0 in cohomology, it is of this form. Then what will happen is that you can show very easily that such a state will be spurious, because q has the form summation L minus n Cn, n contained in Z, plus it will have the form A2 nkm Cn Ck Bm over appropriate choices of for a certain particular choice of these coefficients A2 nkm. So, if q acting, if you write psi as q acting on chi and you require so you would, that means you are requiring psi to be 0 in cohomology, in q cohomology, then if you multiply this by, and you also require, you are also putting the condition that this state has 0 ghosts, Cn chi must be 0 and Bn chi must be 0, you also put this condition for n greater than or equal to 1, this has got 0 ghosts. If you put these two conditions, then what will happen is that if you multiply this by if you you can show that such a state psi is in the range of is in the linear span of the range of the L minus n's. That means you can show that such a psi is contained in the span of the range of L minus n's for n greater than or equal to 1, because the positive values of Ln will cancel out by the condition, by this condition. You see, if you apply, if you look at for example anything like Ln into C minus n chi, suppose you look at this for some n greater than or equal to 1. So psi belongs to this range, but Cn acting on psi is 0, Cn acting on psi is 0, not phi. So this acting on psi is 0 and this, okay, Cn acting on psi is 0 and Cn acting on Bn acting on psi is also 0 for all n greater than or equal to 1, that is they have 0 ghost numbers. So if you act on this by Cn's for n greater than or equal to 1, then what will happen is that it will cancel out with this C minus n's, right, it will cancel out with this C minus n's by using the commutation relation, and Cn acting on chi is 0. So you will get simply Ln acting on chi as 0, Ln acting on that chi is 0. That means that you will get contributions coming from only negative value Ln's for negative values of n, right, you will get contributions from only negative values of n. Likewise if you look at this, a similar thing will hold good, you will get contributions from only yeah. So actually I should write it as alpha, this is the bosonic part, the bosonic part of the Virasoro operators. So it will get contributions only from negative values of n, which means that and of course if you add ln alpha to the term coming from here, you will get ln total, that is the total Virasoro operator for the bosonic fields and the fermionic ghost fields. So it will be a, so you can see that your psi, if it falls in the range of Q, will be of the form L minus n acting on chi n for n greater than or equal to 1, and this is automatically orthogonal to all the physical states, because Ln's annihilate the physical states. Ln acting on phi is 0 for n greater than or equal to 1. So if you take the inner product of psi with phi, that will be 0, because L minus n dagger is Ln, and by moving L minus n to the left you get the result that this is 0. That means that the spurious states, those states which are orthogonal to the physical states, they have cohomology 0. Okay, so so that is the whole theory. Now there is one more result which we have to discuss, namely that if you look at the commutation relations Q comma Bn, this commutator will come out to be equal to Ln. That is because of the very simple reason that if you take A1 nk with Ln with Ck summed over n and k plus summation A2 nkm Cn Ck Bm summed over n k and m. So if you commute with Bn, then then one of the C's will cancel out with the B's on commuting, and you will get Ln, this is Ln alpha, you will get Ln alpha, the bosonic Virasoro operator. On the other hand, if you commute your Bn with this term, one of the these Bn's will cancel out with one of the C's here, and you will be left with a form in a bilinear form in Cn and Bm's, right, you will be left with a bilinear form in the Cn's and Bm's, which will be proportional to, which will be equal, this will contribute to the ghost field LGH n. So if you look at this, this is nothing but it will be of the form Ln boson plus Ln ghost, it will be of this form. This is a quadratic form, this is a bilinear form in the Cn and Bn's, that is with summation C minus n, C, it will be of the form summation C minus m into Bn plus m summed over m, whereas this is a quadratic form in the alphas, bosonic creation and annihilation operators. So from this you can see easily, you can compute, you can show easily using the fact that q square is 0, that Ln comma Lm ln comma lm is equal to n minus m into ln plus m in this relation. That means the anomaly cancels out, the ghost has cancelled out the anomaly. That means what we are trying to say is that if by using the BRST operator we have been able to prove, provided d equal to 26, only then, provided d equal to 26. That means if you want the anomaly to be absent, of course q square equal to 0 only when d is 26, that is also true. Q square is 0 only when d is 26. At that critical value it comes out to be. So, when d is 26, q square is 0, in which case you can prove that, in which case you get the result that there is no anomaly in the total Virasoro operator consisting of the sum of the Virasoro operators of the bosonic field and the Virasoro operators for the ghost field. So, it cancels out miraculously, and the fact that this is based on the fact that the BRST operator q is nilpotent only when d is 26. These are some of the well known facts in string theory. Okay, I will stop at this point. Thank you.